Good day to you from Anagalactic. We have got a solution to a recently posed problem in the prior video: how to get a linear graph of binary logarithms. Well, it's easy to find the curve, and this is from Wikipedia in its article on the binary logarithm, which I'll just expand here temporarily so you can see that y equals log to the base 2 of x. Of course, that's simply the inverse of the exponential function, such that the function of exponentiation takes two arguments. One is the base, which in this case would be 2 rather than 10. And in base 2, you then have an exponent of 2. So the second value in the function is that exponent, which remarkably consists of the domain of the integers including 0. So it is the linear counting numbers with the reflection and the Archimedean. Those of you who have been following my video presentations will know the meanings of those terms. But essentially 0 is the Archimedean of the Euclidean line, meaning its balance. That's because of the two polar infinities of the line, plus infinity and minus infinity, balance on the operator, the numeric operator called add, such that if you add the two infinities of the line, they add to the Archimedean, which then has a numeric value of the additive identity. That's the exact definition of the additive identity, is the central number of the two infinities. Those two infinities are linear infinities, plus infinity, and minus infinity, that add in the same way as all reflection numbers add, such as plus 1 and negative 1. You can visualize that as being equidistant from the center, which therefore is the numeric value of the addition of those two numbers, which, since they're polar opposites, add to 0. They are the same number at an equal distance, and that is actually the definition of the reflection of distance. However, we prefer to call those numbers going to the left, rather than to the right. We call those going to the left the negative numbers. And that creates a balanced operator on add. So that is the definition of add, which is actually defined on the line. And the additive identity is the Archimedean, which is the balance point using the Euclidean geometric term for that point. It is in fact a point, which is 0D, as indeed all points are in the linear system. Now, it turns out that what Euclid failed to do, reasonably so, since it is superpositional, he was attempting to parameterize a planar object, which he called the straight line, which he ended up defining using 2 points. So if you have 2 points on the plane, then the shortest distance, and you can abbreviate that, the distance. It's not really the shortest distance, it is the distance. So he did not need to say shortest. That's redundant. The distance between 2 points on the plane. He was doing everything that he did, at least in the first section. He went on to volume space, of course, with volume objects and volumetrics. That's essentially the second part of elements. But the first part is strict planar geometry that you and I were taught in school that we loved so well, except for the mistakes that we noticed. And then you did whatever you did, I did whatever I did, we each do whatever we do. with the misinformation that was taught to us, force-fed to us, what was considered to be the knowledge base of humanity up to the time of our being taught in school. We were taught several inconsistencies about linear mathematics and, in fact, about linear geometry, but nobody was able to figure out what actually went wrong. How did we get zero? Zero is the death of algebra because you can't divide by zero. The universe actually won't allow it. And if you send any CPU that you can create, a computer brain, if you send a division by zero instruction to that CPU, you will halt the machine and you will have to unplug it. That's called a reboot, and it is required because your machine is frozen. You killed it. And the reason you killed it is because you have a zero in the system. So that is the ultimate mistake, which I finally uncovered and was able to make a major discovery in 2022. Oh, just 4 years and some months ago. I've been on YouTube for 4 years for that reason. Actually, more than 4 years now. So I've produced over 1,600 videos on this discovery of the reparameterization, a 7-syllable word, well, 8 syllables with the reparameterization of the plane to correct Euclid's mistake. It's a little harsh to say it was a mistake, since it resulted in technology. Beginning with linear numbers and linear geometry and linear logic, which is the foundation of science and always has been because of Euclid, that has proved miraculous for technology. And that technology has been rising steadily, really geometrically, over the centuries, so that within the past century, of course, linear mathematics has produced technology that's now capable of destroying the world. So that's as good as you can do. That's really the termination of science. We have achieved all of our goals because now we can destroy the entire Earth because of technology, the wondrous gift, the gift of the gods, you might say if you were a Greek. Oh, the gods are gracious, the gods are merciful. Yeah, there's lots of different kinds of gods. When you say gods plural, you're including Satan, of course. Well, that's who got the technology. That's why we have atomic weaponry and supercarriers. That's why we have super nuclear weapons, the so-called fusion bombs, the H-bombs. Nobody's talked about using the H-bomb yet in the Iranian war and the Russian war, which the decadent West is conducting against the rest of the world, primarily the Russians and the Iranians. But there has been talk lately of the use of tactical nuclear weapons, which are more humane than full-scale nuclear weapons, which can destroy cities, of course, as we know from Hiroshima and Nagasaki, and several coral atolls. There are big holes in the ground where these things have been tested. They were even tested in the air. I think one was tested in outer space. See what it would be like to explode a big destructive bomb and just see what it does, especially to people. That's really the goal of science when you have technology, is to destroy people. So that's not really what we like, and so I never deal with technology, but I always like to mention that you will have to face that someday if you're a real man. That's entirely up to you. If you don't want to be a real man, nobody's forcing you. But if you want to be a real scientist, yes, there are rules that you have to adhere to, such as that you always tell the truth. A scientist is the highest form of human when that scientist is moral, honest, righteous, upright, everything that heaven approves of. Then a scientist is at the head of Islam, and Islam as it is at the head of religion. So that is the ultimate that you can reach in religion, is to be an Islam scientist. That's what I am. I'm an Islam scientist. Born, you could say, in the wrong place. California is certainly the wrong place for an Islam scientist. Everything's stacked against a man of that disposition actually choosing. A man of that election, a man of that commission, he's doomed, and I'm doomed. I don't care. I do what I want. I'm a free man. I don't know what you're like, but I can guess. Well, I am free. Whatever you are, I'm free. And that does not actually weigh very well with you. You are certainly not free, and that's why I produce these videos. So that you can be free, because if you don't have choices to that proportion, you are not free. You only have the choices that you've already been given. Those are your choices, the ones that the elders set up for you. Well, if you want to learn mathematics, you learn Euclid, obviously. Nobody denies that. Nobody denies that. You learn Euclid. And there's an excellent video out that was produced, about 12 years ago that talks about that. I'll have a link in the description for you if you'd like to catch up on how mathematics got to the white world. It actually came through Islam, essentially partly from the Greeks, whom the Islam people recovered when Europe was a death sewer for 800 years. From about 400 AD to 1200 AD, as is pointed out in that mathematics lecture. I'll leave a link in the description again. It's worth seeing how we got our mathematics. Well, it's quite a story. We got it from the Islam people. And that began to occur about 1200 AD. Europe started to wake up. For 800 years, only Islam had civilization. It did not exist in Europe. Nothing happened in Europe for those 800 years, called the Dark Ages. And you could say it's plural. I mean, 800 years is a mighty long time for an entire continent, including England, to be just nothing but a sewer. Just nothing but a cesspool. It was because largely of the Catholics, the false Christians who dominated Europe for that length of time and further, hasn't really quite woken up. There are still literally millions of Catholics. So the human race is in the same condition, basically, that it was 2,000 years ago. When it was given a choice, the world was given a new choice based on a man, unlike any other man who's ever existed, that Islam fully accepts, but the Catholics hate. So that's pretty ironical, I think. And that's why Europe was a sewer. It's because the true Christians were in Iran, they were in Saudi Arabia, they were in North Africa, they were in Spain, and they almost reached Vienna, where Martin Luther noticed that the Muslims were just about to take over Vienna, right in the middle of Europe. Well, about that time of Martinus Luther, who started the Reformation against the Catholics, the Islam people were driven back. The Muslim armies were driven back. And eventually Spain was liberated from the beneficent influence of the Islam Christians. They're Christians. Islam people are Christians. Well, that's of course why the Pope hated them. The Pope hates Christ. Whatever he says with his white robe and his gold mitre and his magic wand and his trillions of dollars. Still the richest organization that's ever been is the rapacious, anti-Christian Catholic Church, still attended by many of our senators and governors and have been Catholic. John F. Kennedy apparently was a Catholic. Well, of course not. He was a politician. But that's enough of our asides. What we would like to discover is the truth of the plane. Because physiologists in the 20th century discovered that we see a movie screen. Yeah, all your nightmares can come true now. It's just purely a projection. You do not see reality, although I'll show you that you actually do. But if you went straight by physiology, we see a Euclidean plane. No, we don't. We do not necessarily see a Euclidean plane. We have to program ourselves to interpret what we see geometrically and mathematically. So we use Euclid. Well, it turns out that that's a huge mistake. And I discovered that fact. them's fighting words. Well, that's science at its best. Is when you actually replace falsehood with truth. That's good, but will it be without a fight? It never has been. It never has been without a fight. There's always a fight. Always a fight. So what is it that is so incredibly inefficient about the linear number system, which is based on Euclid? Our numbers are Euclidean numbers. So I've proved that, and that will be in the book. It will be in the paper coming out by Christmas, so you'll be able to contribute if you wish, even by name if you want to become rich and famous. I will certainly be able to make you rich and famous, although I might be dead by the time you get any money and fame. I certainly will get none, as I'm a failure. You're listening to a failure, but sometimes it's the failures that you should have listened to. That is the case in my case, so let me inform you of what it is that I discovered that is so valuable. It is, in fact, a new number system, brand new. Nobody's ever heard of it. So it's a brand new discovery, very exciting. Everybody should be interested. There have been 4 years now to become interested. That's why I went out to YouTube. But no sour grapes, no hard feelings. I knew walking in what was going to happen. Nothing. And that is what's going to happen. But you're listening. Perhaps you'll benefit from this. Well, let's hope so, otherwise you're wasting your time with me. No, you're not. But the proof is in the pudding, so what do I have over here? Well, let's just expand this a little bit so we can see it just a little bit better. I think you see that that says y equals log to the base 2 of x, and then you see a curve with some points on it. Now, to make a long story short, it took me over an hour of looking for the right graph, and this was the closest graph I could find. About a year ago, when I did this to try to find the graph that I do want, I did find it. It was in an unusual location, and I didn't bookmark it so that I can find the bookmark, and so I lost it. And now I'm just emerging from an extremely frustrated state as I attempted to make a video earlier today, which I did release, vocalizing in no uncertain emotional excess that I was highly disgusted with science today, which of course I am, but I do allot myself a short video from time to time to just vent, because I'm so filled with outrage. But that's not science, and I need to suppress that. I thought you should know that this graph that I found will need to be interpreted so that you know what it says. There is a simpler graph, but I can't find it, and I refuse to do the work of programming to reproduce it. I simply am not oriented towards doing work to reinvent the wheel when the wheel should have been out on the internet for me to find. It's like a needle in a haystack, and yet it's probably the most important graph that you will ever see. So this is the closest that I could come to that. Now, what it is, it's really, there's not much to it. And you can see this is inset in a Wikipedia article. I'm just going to tighten this up here so I can show you the whole thing, because what's on this graph is extremely significant. Now, there's the graph. The formula that you see over on the right is where x equals 8 and y equals 3. And that's the logarithm base 2 of 8. So the number 8, you know, is a binary number. It's a power of 2. Which power? It's the third power of 2. So I'm going to use my pointer now. And there's our handy-dandy pointer. That is the position 8, 3, which is 2 to the third power. This position is 4, 2. And that means that 4 is the second power of 2, so 2 to the second power is 4. This position on the graph, on this curve, is 2, 1, which means that 2 is the first power of 2. 2 to the superscript 1 equals 2. And here's the key. You notice that this does not intersect with 0. This is called the non-Euclidean number system. This is not Euclid. This is non-Euclidean numbers. They're non-Euclidean. They're not Euclidean. They don't occur on a straight line. That means they're non-Euclidean numbers. So the binary number set is the set of non-Euclidean numbers. Now, it may not be the only set of non-Euclidean numbers, and I think you can guess that it's not the only non-Euclidean number set, but what's interesting is there is only one Euclidean number set. And those are the numbers 1, 2, 3, 4, 5, and then as high as you like to go. Those are the Euclidean numbers that occur only on a straight line. These are the numbers that only occur on a different kind of line called a curved line. And you know from the family of curves that that curved line can only be one of 4 different types of line. But it is on a continuum. This curve here is actually it's hyperbolic, and it is an inverse graph. It's the inverse of exponentiation. So what I want you to see here is the relationship between 2 component numbers, all of which are on that curve because it's a 2D curve, and 1 component numbers, which you will see using our handy-dandy pointer here, that these numbers on the x-axis are single component numbers called linear numbers. And the numbers on the y-axis are also linear numbers. So those are single component numbers. But all the numbers on the curve are 2 component numbers. Why? Answer that question in your mind now. It's a quiz question. Why are those 2 component numbers? It's because they exist on a curve. And all numbers that occur on a curve are 2 component numbers, and in fact, this graph proves it. What is fascinating is this graph never intersects the y equals 0 axis. Y never equals 0. There is no 0 for the result of a log base 2 of x. So log to the base 2 of x cannot equal 0. So y cannot equal 0. So this graph actually proves that because it's asymptotic to the y-axis. It's asymptotic to the y-axis. That means it never intersects with the y-axis, but it gets closer and closer to the y-axis infinitely. Infinitely. And that is infinity. So that line goes to infinity. Now, when you trace it up this way, you get the positive binary numbers, the first of which is 1. 2 to the 0th power. 2 to the 0th power sounds like kind of a puzzle. Can you raise a number to the 0th power? Yes, you can. And it has been proved that you can do that. 0 is not in the system, but it is in the linear number system, and it's just a coincidence, it would seem, that the linear numbers, which are all the numbers that exist on a line, if you include 0 in order to get the reflection numbers going negative, these would be the negative integers. They're simply the same numbers on the other side of 0 on the horizontal axis, correct? It's treated as anti-distance to the proportion that the positive x-axis is treated as distance, which the Greeks did not know anything about. There's no such thing as negative distance. So the negative numbers were not even discovered until centuries after Euclid. Neither was 0. So they had no 0, and they had no negative numbers. And in fact, in the universe, there is no 0, and there are no negative numbers. I proved that in 2022. Now you may ask, and I would say reasonably so, how can it be that there is a number system that has no 0? Well, it's because the plane does not need to be parameterized with 2 lines. If it is parameterized with 2 lines, then you're stuck with 0 because 0 is on the line. If there are 2 lines on the plane such that they intersect at right angles at 0, now you can't get rid of 0 because it's the origin of both the vertical aspect and the horizontal aspect. So now you definitely have a 0. You see, you can have numbers without 0. The counting numbers for apples, there's no 0 in the counting number system. You can look that up in Wikipedia. It has been known, basically for centuries, that there is a subset of the linear number set that is nothing but positive integers. And those are called the counting numbers. There's no 0 because there's no such thing as 0 quantity. 0 is an imaginary number, and that is exactly how Euclid defined it geometrically. It's an imaginary point. But what's strange about the straight line is all the points are imaginary, because all the points are exactly of the same dimensionality as 0, which is 0 dimensionality, which means it's not there. Which means that this is a relativistic system based on quantization. That's a lot of information, but this is the beginning of the documentation for my book. So you're getting this straight up, but it does have to be precise. This is formal. So you see the numbers here. I'm using my pointer again. I think you can see that we are pointing at 8, 4, 2, and 1. However the line continues, you can have an exponent. You can have an exponent, which is what is shown on the y-axis. Those are the exponents. And this is what I wanted you to see, is this vertical line. Because look, it has all the integers on it, including 0. So 0 is at the center, and here are the integers, 1, 2, 3, 4. These are the numbers that produce binary numbers by exponentiation of 2. So 2 to the 0th is 1. 2 to the first is 2. 2 to the second is 4, and so on. And this is a number line. It's a curved line, and it goes below the abscissa. It goes below the y positive. It goes into y negative. So you can have a negative exponent of 2. Do you know what 2 to the negative first is? It's 1/2. So this is Zeno's paradox. So here is halfway to the center of a circle. That circle has a value of 1/2. 1/4 of the way to the center, you have a circle whose circumference is equal to 1/4, 1/8, 1/16. These are the reciprocals of the positive binary numbers. So for every 2, 4, 8, that would be exponent 1, 2, 3. You have negative 1, 2, 3 for 1 over 2, 1 over 4, 1 over 8. So this is 2 over 1, 4 over 1, and 8 over 1. These are numbers that are in relation to 1. On this line, these numbers, called the linear number set, actually the integers, it's only the integers, and there are only these integers produce the binary numbers. So there's actually nothing in between these numbers. These are fixed numbers with nothing. There's nothing in between 0 and 1, because there's no number between 0 and 1 for that exponent of 2. But there is a number for 2 to the 0th. 2 to the 0th is 1. This 1 is the symmetrical center of this line. So it is the Archimedean of this curve. What I have proved is that this curve indicates all the circles on the plane to infinity. So that reparameterizes the plane, not using linear numbers. It uses these fractions, and they are fractions. Fractions are two-component numbers, as you can verify visually. And now we need a slightly different diagram so I can show you those fractions. What we want to show is this is the number system for the plane. But you can't use a Euclidean point to begin. When you have an empty plane, instead of starting with Euclid's point, you start with a different point that I discovered. It's the non-Euclidean point, and this departs completely from Euclid from this point forward. Very nicely placed pun there. From this point forward, from the point of discovery that I made in 2022, we now have a brand new definition of the point. A non-Euclidean definition where there is only one point in the whole system. The Euclidean system is made of points. It's made of points on the line. It's made of points on the plane. It's made of points in 3D space. And it's made of points in SpaceTime, which is 4D. So all the way up to SpaceTime, all the way up to the cutting edge of physics as it exists right now, this day, 2026, everything is made of points. And all of your numbers are Euclidean point numbers. All of them are. They don't exist. They're in derivative space, actually. I proved that in 2022 with two theorems that changes geometry forever. With the integral system, much superior. The linear numbers cannot be discarded because they are the representable numbers, which means they're the computable numbers. But that's not quite true. Do you know which numbers of all the numbers in the linear number set, said to be infinite for the real numbers, but that's actually not provable. For the linear number set that science has used forever, that Einstein used, which everybody uses to this day, in that number system, which numbers do the computers use? Do you know? Do you know? Don't say if you don't know. This is a quiz, so I'll give you the answer. I'm a computer scientist. I'm actually something of an expert in this area. I did study this at a very high level. So, just capitalizing on the work of my predecessors, none of which I've improved on. These are the genuine results of science. What are the numbers that go into your computer that make everything all the way up to AI work? Which numbers? Does the number 3 exist? Yes, that's representable. Is 1 over 3? No. No, 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 no. 1 over 3 is not a number. That's not a number. It's not a number. It's 1 over 3. That doesn't reduce to a linear number. 1 over 3 is a two-component number, but is it binary? No, it's not, so it's not a number at all. Only binary numbers are numbers that a computer can see, called representable. Representable means the computer can see it. Can the computer use it? That's called computable, computability. There's representability, which only the binary numbers can be seen by a computer. Which ones can they use? The same numbers. Okay, they can use those numbers. How? How is that done? Well, you can study that for a long time. I just throw out the question to get you to think about it. But that's actually not what we need to concentrate on now. The important aspect of what I just put out on the table, this is all well known. The binary number set is the only set of numbers that a computer understands. And it's the only numbers that it can represent in the system. Now you may know that 1 over 3 can be partially computed. That is, it can be turned into a value. But it depends on what you mean by value. It is a repeating decimal, which means that it goes to infinity. As a quantity, as a value, it has an infinite representation. In other words, it cannot be computed. To get a computation, you have to get a number that the computer can see. And it can see the 1, and it can see the 3, because 3 is a positive, it's a whole number. And it can see all the whole numbers because, well, I'll just say it can. It can see all the whole numbers. And that does make sense. You should be able to figure that out. But you can look all this up to make sure of what I say. I'm not making any of this up. I'm just catching up so I can tell you what comes after what we currently know that improves on what we know. That's called science. The progress of science. I'm contributing to the progress of science. Now, since the computable numbers and the representable numbers are both binary, it's identical from the point of view of the computer. But you can set up an operation from which the computer cannot compute a representable number. And if you give it the number 1 over 3, which we're taught in school is a number, the computer disagrees that 1 over 3 is not a number, for the reason I just told you. And that's what the universe says. Nobody can argue with that, although it has been violently argued for well over a century by theoretical mathematicians who deal with something known as Zermelo's something. Anyway, it has to do with Cantor and some other guys, Dedekind, who tried to show that the quantized line, which is the Euclidean line, it has to be quantized or you can't have numbers. So it's infinitely dense with points. It can't be infinitely dense with points. If it were infinitely dense with points, there would be no numbers, because the numbers are points. So that's why I went into such extraordinary geometric detail to show you what a linear number is. It's a point. Not anymore, it's not. I changed that. I found out what Euclid did wrong. It's the point. So what is the true definition of a point? Well, the false definition of a point is, first of all, you have to have 2 of them. You have to have 2 or there's no relativity. And if there's no relativity, there's no distance. And that's the same thing that's tautological with the state, that is, it's identical with saying that the shortest distance between 2 points is a straight line. Well, what's the smallest one of those? Nobody knows. You have to go down to the physical scale to get the smallest distance between 2 points. That, of course, as you well know, is called the Planck length. The Planck length. the Planck length is the shortest distance between 2 points in the physical universe. You may wonder about that. A lot of men have. It's called the quantum paradox, and it's the basis of the most amazing, complex of contradictions and paradoxes that the human mind has ever encountered. Is the shortest distance between 2 points, first of all, can only be indirectly measured. But when you say that you've discovered the shortest distance between 2 points, what you're saying is that there is a space between those 2 points which cannot be divided, that it's absolute. And that may remind you of light speed. So what is this shortest distance, and why is the Planck length so significant? Because it defines the quantum jump in linear space. The Planck length is a distance. It's called a length because it's at such small scale. It's the ultimately small scale. It's the infinitesimal of the line. So the Planck length is the infinitesimal of 1D space, which is considered to be space. Is that true? No. It's a derivative of space. A straight line is a derivative of space. Space has more dimensions, but a straight line only has one linear dimension. So it's a subspace of space. That is, the 1D object called the straight line is a subspace of volume space. Volume space is physical space. It's what we see, feel. You can put your hands through empty space. That's space. Well, it's not on a line. So it's artificial. So what is space really? Well, if it's volume space, it's spherical. If it's on the plane, it's circular. So Euclid missed, he goofed. Unbelievable thing to be able to say after 2,400 years of Euclid is for this desert professor to come along and say, I just made a discovery using pure mathematical logic that proves that Euclid was wrong and the number system we're using does not match the universe. It can be made to match the universe because it's parameterizing the same it's parameterizing a subspace of space. But if you begin with a straight line, you're stuck with the Euclidean point because the line is made of points based on the Planck length, which is the quantum jump from 0 to 1. It's the quantum jump from 0 to the closest 1. To scale the line, you need to scale the unit. Well, you have to scale it to the smallest unit, and it cannot go to 0. Otherwise, you don't have any distance between any 2 points. But on a line, if you have a distance between 0 and 1, that's the unit of the metric, which is distance. So now you have the unit, which has to be 1. That's the definition of what 1 is. It's the smallest unit. So the smallest unit of distance is fixed for the whole universe if you do that. Well, what's the smallest unit? That was debated for decades, and it hasn't gone away because there's a contradiction involved in quantizing the line. Because now there's nothing in between 0 and 1, and that's called the quantum jump. Because there are no numbers, there are no points in between those 2 points. What Dedekind and Cantor were dealing with when they tried to continuize the straight line, to make it continuous, so that there's an infinite density of numbers, you can't. And that was the net result, which they should have figured out right away, but they were desperate because they needed a continuous function for linear space. There is no such thing. The best you can do is the calculus. The best you can do to continuize, to make continuous what is ultimately quantized. Well, if you quantize, you're done with continuity. Either you have a quantum jump and you just keep jumping so that you have a unit for your metric of distance so you can make a measurement. You have to have one. Well, you have to have an origin between point A and point B where one of the points has to be 0. Otherwise, you can't get to 1. There has to be an origin so you can make the quantum jump from nothingness. So you're stuck with 0. 0 is always at the frame of reference. It is the frame. It's the origin of the frame of reference. 0 is at the vertex of the light cone for spacetime. It's a 4-component 0. It's 0 time, it's 0x, it's 0y, and it's 0z. There are 4 zeros. That doesn't exist in the universe. I proved that. The binary numbers don't have a 0. What does this have to do with computation? Why are these two facts important to juxtapose? That the computer number system has no 0. There is no 0 in the computable number system. The binary number system is the computable number system. It's what you can do mathematics with. You can only do mathematics consistently using binary numbers. There is no 0. Let me show you again so you will be reminded of what I'm saying. That is not a straight line. It is the graph of the binary numbers. So those are the numbers that a computer uses. Those are the computable numbers. So what about numbers like 1 over 3? Well, they're part of the linear numbers because we say so. Is that justified? Is 1 over 3 part of the linear number set? No, it's not. 1 over 3 is not a number. Why? It's because you're proportionalizing two quantities with 3 in the denominator. 3 in the denominator. 1 over 3 is a 2-component number. It's called a rational number. But not all rational numbers are binary numbers. Binary numbers are powers of 2 rational numbers. Powers of 2 rational numbers are restricted in the numerator and denominator to whole numbers. Those are rational numbers. I don't know if you knew this, if you were taught this very carefully in school. It's really rather strangely taught. The rational numbers are numbers like 21 over 7. Or really, 22 over 7 was an early approximation of pi. 22 over 7 is remarkably close to the value of pi, considering it's a simple fraction. But it is not a rational number, because 7 does not produce a rational number. So why do we say that 22 over 7 is a rational number? It's because both the numerator and denominator are whole numbers. But you have to leave it that way. For instance, if you have 1 over 3, you have a rational number. But is it a binary number? No, it's not. Is 3 a binary number? It's not. But all the whole numbers are representable. And there's a reason for that. But it's strange. The positive binary numbers are 1, 2, 4, it skips 3. And then it goes to 8, it skips 5, 6, and 7. And then it goes to 16, skipping all the numbers between 8 and 16. But these are simply the values for the numerator, because all those numbers are over 1. They're proportion 1. And we are taught in school that all whole numbers, proportion 1, reduce. And there's the key. You have to reduce it. Because 1 over 3 is a 2-component number, But the computable numbers are one component numbers. They always are. Is that true? Yes, because even though the binary number system is a two-component number system, only the linear versions of those numbers are computable. So you can have 2 over 1 and 4 over 1, which are two-component numbers, but in order to manipulate them, they have to be linearized. And that's why they're magic numbers. Because 2 over 1 reduces to 2. But you're reducing it so that it's no longer proportional to 1. You're just saying it's a counting number. So you always get a counting number from the whole binary numbers. Even though they're two-component numbers, they're all over 1, and therefore they are legitimate linear numbers. Even though they're in two-component form, they can all be represented as one-component numbers because they're all over 1. Everything changes when you go to the fractions. Because if you go less than 1, which I'm showing you on the graph, is this part of the curve. Those are numbers less than 1. Everything above the line is a number greater than 1. And the number that's on the line is 1, which is not the additive identity, it's the multiplicative identity, as our mathematicians have identified that by a name. They call that number the multiplicative identity. Why? You could state in a couple of ways, at least, why 1 is the multiplicative identity. In order to know why 1 is that peculiar number, the center of the system, you merely need to compare it with the additive identity, which is defined the way I told you, on two infinities that add to 0. Here, we have two infinities that multiply to 1. And that is so profound, I want to stop and let that sink in. Let me say that again. The center of the linear number system is 0 because its two infinities add to that number. On this line, representing the binary numbers, the two infinities multiply to 1. Now, the identity number of a number system has some very useful qualities. In the case of addition and subtraction, subtraction being the linear inverse of addition, when you, first of all, when you add the two infinities, plus infinity and minus infinity, they're balanced on the identity number. But now you have a number set that's in between the two infinities whose center is 0. So you can jump 1 in both directions, 2 in both directions. If it's distance, they're polar opposite distances, +1, +1. What we do in order to utilize the function of add and subtract is we say that when you jump this way, it's +1. It's a distance 1. Whereas this jump, -1, is the reflection. That's the geometric. So it's given a negative sign to show that it's different in direction on the line. Here, and I didn't complete what I wanted to say about addition. If you add two numbers, 1 plus 1 equals 2. Well, 1 plus 0 equals 1. And that makes 0 special. Also, 1 minus 0 equals 1. And if you have 0 as the first number in subtraction, you can also do that, so that 0 minus 1 equals -1. So it's consistent and closed for addition. So the line is consistent, coherent, and closed for addition. And that's why you need 0, is so you can obtain closure on infinity. So you have to have the 0 in order to balance the two polar infinities. That all should make sense. I know this is so difficult. I know how hard this is to hear. It's so challenging. But please pay attention, because the next step is critical. 0 has no effect on the operator. And there's only one operator on the line. It's add. I just proved it. This is actually my first theorem called, well, we'll get into that later. Yeah, that'll be in the paper in the book. By Christmas, I promise. All right. So what does this line show? This is a curve. It's not a straight line, but it represents the binary numbers. The line going up and down, called the ordinate, called the y-axis in our language. That number is the integers. And what this graph shows is that the integers are the closed set that comprise the domain of the binary exponents, so that you can have 2 to the power of any of the integers, including 0. That's critical, because 2 to the 0th is the center of the binary system, and you can see it. This curve below the line, which is asymptotic to the y-axis, has a fixed geometric and mathematical relationship to the positive binary numbers, which are on this part of the curve. And I'm not using the pointer. Down here, these are the fractions going from 1 to 0. Okay, it's 1/2, 1/4, 1/8, 1/16, and finally, at the end, 1 over infinity, which is now a rational number, using an imaginary denominator. This is part of my second theorem. I'm giving this to you in a nutshell using this graph because I can do so, but this has got to frustrate you, and I'm so sorry. But you're going to have to think now. You're going to have to do it. So listen carefully. 1 is the center of the two-component number system to the proportion that 0 is the center of the Euclidean system. And those are the two identity numbers. So you can either parameterize the plane on a 0 point, or you can parameterize it on this Archimedean of 1. So what is that number 1? Because it's not a point. What is it? This is the curve showing all the concentric circles on the plane. The value of the circumference of this circle is 8. The value of the circumference of this circle is 4, and so it's inside the 8, contracting. This is a circle with circumference 2, and this is the circle with circumference 1. That's the center. That's a point, except it's not a point in the Euclidean sense. It has an interior. That interior is quantum space. Is it really there? That will be the subject of the next video. We're coming up on an hour. So I've just shown you that there are 2 distinct number systems for the plane. If you use the Cartesian XY system, you will have to conjugate the x and y values using the Pythagorean theorem, which gets you into a trap, because there's no such thing as the square root function. The square root function is transcendental, and if you try to take the square root of 2, you'll find out what the Greeks found out, the Pythagoreans, to their utter shame and chagrin, many of them reportedly, although this is probably myth, committing suicide, because that ruins the universe. Because you cannot get a value for the square root of 2. And so a square with height 1 and width 1 has no hypotenuse. And so you cannot use the Pythagorean theorem. It doesn't work. What does work is the Pythagorean theorem in spherical space. That will be in the next video. Thank you for tuning in. This is Anagalactic, bringing you the secrets of the universe. We'll be right back. Thank you.